Okay? So as part of the warm-up, what we're going to do is find our additive inverse. So the additive inverse of each term is its opposite. So you want to find the additive inverse of each term, which is essentially like saying its opposite. So the additive inverse of 4 is -4. The additive inverse of x is positive x. The additive inverse of 5x is -5x. And the additive inverse of 8y is -8y. In parts 5, 6, and 7, we're kind of taking what we did yesterday with the variable expressions. And yesterday what we did was we substituted in for a variable with a number. Now, instead of replacing a variable with a number, we're going to place a variable with an equation. So everywhere I have the letter x, I'm going to replace it with 2y minus 1. So everywhere I have an x, I'm going to replace it with 2y minus 1. Sorry, I need to be able to write again. So we have 2y minus 1 plus 2y equals 3. Combining like terms, 2y plus 2y is 4y. Minus 1 equals 3. Add 1 to both sides and you get 4y equals 4. Divide both sides by 4 and I get y equals 1. So again, our goal is to solve for our variable. In number 6, we're going to replace the x with 2y minus 1. This time you have to be a little bit more cautious because we have to make sure we distribute the negative into the problem. So I have y minus 4y plus 2, because a negative times a negative is a positive, equals 8. Combine like terms on the left, so y minus 4y is negative 3y. We're going to subtract 2 from the right, and we get negative 3y equals 6. Dividing both sides by negative 3, I get y equals negative 2. Similarly, in number 7, we're going to replace the x with 2y minus 1. So I have 2y plus 3 times 2y minus 1 equals negative 5. We're going to distribute the 3. Combine like terms. Add the 3 to the other side. Divide by 8. And I get y equals negative 1/4. So what we're going to do now is extend that idea one step further. So in the previous 3 examples, they told me what my x was equal to, and then we plugged it in and solved. Now I have 2 equations, and I have to solve for both x and y, and I have to set it up by myself. So this is called the substitution method. Basically what we're going to do is substitute one variable from one equation into that same variable in a second equation. So what I want to do is look for the variable that has a coefficient of 1. So what I mean by that is if you look at this first equation here, I have x, 3y, and 12. So the variable x has a coefficient of 1. So what I'm going to do is solve for x in that first equation. So I'm going to rearrange my terms to solve for x, giving me x equals 12 minus 3y. So now, just like the warm-up, I'm going to replace the x in my other equation with 12 minus 3y. So I'm going to replace that x there with 12 minus 3y. And I'm going to solve for y. So 23 divided by 10 is 2.3. You could also keep it as 23 over 10. That fraction will not reduce. What? Yes, thank you. There we go. So now you have to solve for x using the y you found. So what we're going to do is plug that y back in. So x is equal to 12 minus 3 times 3.3, or 33 over 10. And we get y is equal to 2.1. Or sorry, x is equal to 2.1 when y is equal to 3.3. So we're going to have 2 variables and 2 solutions for all of these equations. This directly goes back to chapter 3 before we left for break. So this would be, if you graphed both of these lines, this would be the point at which the 2 lines cross each other. So these are intersecting lines, which is an independent solution with one solution, and that one solution is this point of intersection. In number 2, you could solve the bottom equation for x or y, depending on which variable you wanted. There's not necessarily a right or a wrong, since both have coefficients of 1. Since we've been solving a lot for x, let's solve for y. So we'll say that y is equal to negative 12 minus x. We're going to replace y in the top equation now, since we solved for the bottom. So you get 2x minus 3. And instead of y, we're going to replace it with negative 12 minus x. Equal to 6, and then you're going to solve for x. A negative times a negative is a positive, so you get 2x plus 36 plus 3x equals 6. Combining like terms, 2x plus 3x is 5x. Subtract 36 from both sides. Divide by 5. And you get x equals negative 6. We take that value, plug it back in, and solve for y. So you get negative 12 minus a minus 6. So that turns the minus a minus to a positive, or negative 12 plus 6, which means that y is also negative 6. In number 3, I'm going to add that y to the other side. So I get 3x equals y. I've now solved for y. So I'm going to substitute 3x in for y in the bottom equation. So I have 4x plus 3 times 3x equals 26. When you substitute into the other equation, you should always end up with just a single variable. So if you substitute and you have an x and a y still, you substituted incorrectly. So 3 times 3 is 9, so 4x plus 9x equals 26. 4 plus 9 is 13x. Divide both sides by 13, and x equals 2. Since x equals 2, y is equal to 3 times 2, or y is equal to 6. So again, 1, 2, and 3 all represent intersecting lines. These are independent systems with one solution. If I were to graph them, their graphs would intersect at those x and y values I found. We can also apply this method to word problems. So now what we have to do is construct our equations from the word problems and then solve. So it says at Rinaldi's Pizza, a soda and 2 slices of pizza cost $10.25. A soda and 4 slices of pizza cost $18.75. find the cost of each item. So what we have to do is define the variables. So we could say that X is a soda and Y is a slice of pizza. So that one soda plus 2 slices of pizza is equal to $10.25. And 1 soda plus 4 slices of pizza is equal to $18.75. So now I can choose either the top or bottom equation to solve for X, since both my X variables have a coefficient of 1. So maybe I solve the top equation. So I have X equals $10.25 minus 2Y. And I'm going to replace X in the second equation with $10.25 minus 2Y. Combining like terms, I get 10.25 plus 2y equals 1875. Subtracting 1025 from both sides, you get 18.75 minus 10.25 equals 2y. So 2y equals $8.50. Or 1y, or 1 slice of pizza, cost $4.25. Once I know the slice of a pizza, I could find out the cost of a soda by plugging in the slice of the pizza cost back in. So we'd take $10.25 minus 2 slices of pizza at $4.25, and we see that a soda costs $1.75. In the second example, it says you can buy CDs at a local store for $15.49. You can buy them online for $13.99. However, you pay $6 for shipping. Find the number of CDs that you can buy for the same amount at the two stores. So we'll say that Y is the store and X is the number of CDs. So at the store in person, it's $15.49 a CD. At the online store, it's $13.99 a CD plus $6 to ship it. We want to know, when does it matter where you go? So I want the online store price to equal the in-store price. So we're going to set the two prices equal to each other and solve for the number of CDs. So Y is equal to 15.49X. So we're just going to replace the y in the second equation with 15.49x. And then get my x's on one side. So we'll subtract 1399 from 15.499. And we get that we have 1.5x is equal to 6. Divide both sides by 1.5. And I see that if I buy 4 CDs, the online price and the in-store price will be the same. We don't have to solve for y in this problem because it didn't say find the cost. It just said find the number of CDs. So we don't actually have to solve for y in this problem. Questions, comments, concerns? Okay, your homework is the next page in that packet, front and back.